In this video, we're going to take a look at Chapter 9, Center of Mass and Linear Momentum. So first, the reason that we deal with the center of mass is oftentimes the motion of rotating objects can be complicated. So as pictured here, imagine a bat flying through the air, but it's also rotating as it's flying. And so looking at any one particle on that bat, it would be kind of complicated to describe its motion. However, there is a point at which the mass of the bat rotates around, and that point is what goes through the parabolic path, just like any object that we would throw and expect to see go through that parabolic path. And so we can focus on this center of mass, and it allows our calculations and all of our physics to simplify a little bit. So to calculate the center of mass, we have to look at it in different dimensions. So let's just start simply with one dimension and just two objects. If we have one dimension and two objects, we can calculate the center of mass using this equation, equation 9.1, where the center of mass is going to equal m2 divided by the sum of m1 and m2 times the distance that separates them. And you might ask, well, why is there only m2 and not m1? Well, that's using basically what we're doing is we're taking one of the masses and making that our axis of rotation, and so there's no torque being applied by that mass. Now, just more simply, looking at any x component, so let's say we have our x-axis here, and we've got a mass here and a mass here, and they each have their positions, so this is x1 and this is x2. We can find the center of mass by looking at the mass 1 times its position, mass 2 times its position, divided by the sum. When we take the first position to be 0, so if we call this 0, that's when we simplify to this first equation. Now we can expand this equation to 3 objects, 4 objects, 5 objects. We just keep adding more terms on the top and more terms on the bottom. And so this will work for any type of 2-mass system, 3-mass system, 4-mass system, as long as they're on one axis. Now, let's say we have an infinite number or some arbitrary number n. We can add all those up using these individual terms here and dividing by the total mass. So we a lot of times will write the center of mass is really 1 over big M, the total mass of the object, times the sum of all the little masses. Now we can do this on the x-axis, we can do this on the y-axis, and we can do this on the z-axis. And then that gives us a point, an x-y-z point, that tells us the center of mass of that object. Well, we can even combine this to be even a little more concise to say that the r vector, the center of mass of the r vector, is simply equal to 1 over m, this is the total mass, times the sum from 1 to however many objects we have of the mass times the position vector, the r vector. All right, now let's take this to, let's have a solid object or a solid body, and now we have an infinite number of little chunks that we want to add up. Well, when we want to add up an infinite amount or an infinite sum, we get integration, and this is where the calculus comes in. So we can look at the x center of mass is the total mass, the reciprocal of the total mass, times the x component dm. And then y center of mass, y component dm, z component dm. All right, so on and so forth. Where big M is the total mass and dm, that's talking about how our x changes with respect to m, and we need to integrate that. So use a little density and volume, bring this in here to say, well, dm over dv, the change in the mass over the change in the volume, is the same ratio as the total mass over the total volume, or the density, and we can say that the x center of mass can be found by using volume calculations here of 1 over the volume times the integral of x dv. Now keep in mind, dv and x, they may not just be simply that variable. These could be other functions that we're going to have to deal with, but these are the formulas and the equations that we're going to start with. All right, now you can bypass one or more of these integrals if the object has symmetry. All right, and so that's going to depend object to object, but symmetry can help you simplify some things. All right, you can take a look at this checkpoint here, pause the video, try to answer these questions real quick, and then move on. Another example here, and I'm not going to spend too much time on it, if we wanted to go through and find the center of mass of an object where we have a disk and we remove another disk, we would have to look at the center of mass of each of those objects and combine them in a way to get the new center of mass of the object. So let's move into looking at Newton's second law for a system of particles. And we know Newton's second law says that the net force on an object is the mass times acceleration. Force is a vector, acceleration is a vector. But the key here is this is really the acceleration of the center of mass. Now, up until this point, we've been dealing with all objects. Essentially they're point masses, so this hasn't really affected us at all. But we want to more clearly define what Newton's law tells us, and it tells us that the net force on an object denotes and kind of quantifies the acceleration of the center of mass of the object. All right, and so we know that the net force is the sum of all external forces, and M, big M here, is the total mass for the closed system. All right, and A sub com is the center of mass acceleration. So when we're looking at center of mass acceleration, we can look at just the net external force is the mass times acceleration. So a nice example here is billiard collisions. So if we have the billiard balls hitting and bouncing off of each other, we remember that those forces are only internal, and so therefore the net force on the object or on the whole system is zero. So the acceleration of the center of mass of the system is going to remain zero. And so any collision in subsequent collisions after that are going to happen such that the center of mass, the center of all the masses of the balls, is going to be zero. All right, think about a bat, a baseball bat, where the acceleration is equal to baby g, where we were just throwing the baseball bat earlier, and so the center of mass follows the gravitational trajectory. All right, it follows that parabolic path. All right, another way you can think of this is an exploding rocket. Any of those explosion forces are internal, so only the gravitational force acts on the system, and so the center of mass follows that trajectory. And so we have it pictured here. So imagine a rocket that's following this trajectory, and then all of a sudden it explodes. Well, we get fragments going up and over and down and all over the place, but the center of mass of all of those objects continues along this path. And so the center of all of the mass of the shrapnel that's flying through the air is still following that parabolic path. Not any given piece, any given shrapnel isn't going to follow that parabolic path, but the collection of all of them is going to still continue along that path. Here's another checkpoint. Pause the video, read it, take a look at the answer here. Now let's move into linear momentum. We know momentum is defined as the mass times velocity, but once again, momentum is a vector, and because velocity is a vector, so the direction here matters. Now, the time rate of change of the momentum of a particle is equal to the net force acting on the particle, and it's in the direction of that force. So another way that we're going to define momentum here that's going to be a little new is that the force, the net force, is the time derivative of the momentum function. All right, and so really this is Newton's second law here, rewritten in terms of momentum. Okay, and so we can sum up the momentum for a system of particles, and we can find that the total momentum is the total mass times the velocity of the center of mass. Okay, and that's talking about the linear momentum of a system of particles. Using this equation that F net is the change in the momentum over the change in time, which is kind of our impulse equation that we used back in AP Physics 1, we can focus on the momentum of an object, have a function for it. We know its derivative is going to give us the net force at that given time or a given position, whatever it may be. Now, without a net external force, the total linear momentum of the system cannot change. So we have to have the momentum consistent as long as there are no net forces acting on it, and those are net external forces. So when we start colliding objects, we have this idea of impulse, and we know impulse is the change in momentum, and we're going to define it as J, all right, and it's going to be a J vector, and we can find this by integrating the force with respect to time. Okay, now we know conceptually to decrease the effect that, say a body encounters on a collision, we want to increase the time. That's why we have airbags. That's why we have seat belts. That's why we pole vault onto a mat. That increases the time of the collision because the change in the momentum is going to be the same. But if we increase the time, we decrease the force. And so we say that the change in the momentum vector is equal to this impulse, this new idea impulse, which we're going to call J. All right, and if we want to find the average, all right, average force on that, we can find the impulse average force times the time interval, and that'll give us another way to look at this is the area under the curve here. All right, the area under that curve, that force curve, we can find the average force and then multiply by the time interval there. Okay, read this checkpoint, pause the video, try to answer these questions. Now, for a steady stream of n projectiles, so say this is a machine gun that's shooting bullets into a target, or it could just be, it could be anything with a steady stream. It could be a beam of electrons that are hitting a screen. We can say that each undergoes a momentum change of delta p, all right? And the impulse is going to be the number of particles times that delta p. Now, we need this negative sign because of the direction here in the change of the impulse. So finding the average force using these equations, we can end up with the average force is a negative n over delta t times m delta v, where delta v is simply just the negative of the v that these projectiles are coming in. And so that's if it stops. Now, if it bounces back at the same speed, well, then we have to have negative 2v. So think about it, coming in at 5 and bounces back at 5, its change is actually negative 10. The product of this n number of particles times the mass of one particle is going to give us the total mass of all of those collisions. And so we can write the average force as this change in mass, all right, which could be this total mass here, all right, divided by the time interval times the change in velocity. And so I want you to take a look at this checkpoint 5, pause the video, try to answer these questions. Now we know linear momentum is going to be conserved as long as there's no net external force acting on the system, and so we call this a law of conservation of linear momentum. Now keep in mind this is linear momentum, not rotational momentum. Rotational momentum or angular momentum will also be conserved, but that's separately. Okay, and so as long as there's no external force, we know that we will have conservation of momentum, and this also accounts for all the parts. Now the momentum of each little piece in the system could change, but the sum of all the momenta is going to be constant. And a key point here is don't confuse momentum and energy. All right, sometimes they are both conserved, but oftentimes energy is not conserved, but momentum is. Now, when we deal with specific collisions, we have two different types of collisions. We have elastic collisions and inelastic collisions. Elastic collisions, total kinetic energy is unchanged. So we have conservation of kinetic energy. All right, a useful approximation for common situations. All right, now it's not real. We can't have a perfectly elastic collision, but it's close. And so we usually lose some energy, through friction, sound, light, whatever it may be. But elastic collisions are close to a lot of everyday collisions, and that's why we study them. In elastic collisions, some energy is transferred, all right? And so we lose some energy in sound, deformation, in, changing masses, stuff like that. So completely inelastic collisions, the objects stick together, and there is a huge loss in kinetic energy. Okay, the total kinetic energy of the system before is much, much greater than the total kinetic energy of the system after. Now, in inelastic collisions, we have this equation, that the momentum before is equal to the momentum after. Completely inelastic, we can change that to the sum of the masses times the common velocity. All right, now keep in mind these are center of mass of the objects, and we're going to talk about the center of mass of the system in a little bit. But these are the velocities of those objects before the collision and after. Now, if we want to look at the velocity of the center of mass of the system, keep in mind, of the system, that's going to equal the momentum divided by the total mass. All right, now we can look at that as, the momentum of the two parts here. But, we can look at what's the velocity of the center of mass going to be. Well, we take the momentum divided by the total mass, and that gives us the velocity of the center of mass. Is it moving to the right? Is it moving to the left? Or is it just simply zero? Is it staying stationary as, two cars come to a head-on collision type thing? So take a look at this checkpoint here, read over the questions, and pause the video, try to answer them. Elastic collisions in one dimension, the both momentum and kinetic energy is going to be conserved. So these two equations are actually kind of helpful. We didn't have equations quite like this in AP Physics 1, even though we could have, but this is simplified for us very nicely. Now, the situation here is looking at before we have some object moving in and it hits a stationary target, and then after we, both are flying off in some direction. And so we can find the final velocities of those two based on this ratio of that initial velocity coming in. All right, now, what are the implications of this? Well, if we have equal masses, then the final velocity of 1 is going to be 0. It's just going to stop dead in its tracks. And the velocity of 2 is going to be equal to the initial velocity of the object coming in. All right, massive target, so where M2 is much, much bigger than M1, the first object just bounces back and speed is mostly unchanged. All right, for massive projectile where, the final velocity is almost initial to the final velocity is almost equal to the initial velocity, in that, if we have a really big projectile and a small target, the projectile's velocity is not going to change by very much. So using these equations, we can also do some simplification, and when we have two objects moving at each other, we get the final velocity for V1 to be this, and the final velocity for V2 to be that. All right, and this kind of simplifies, puts the two equations together. You don't have to use these. If you want to start with conservation of momentum, conservation of energy, then that's fine, and you can do the algebra yourself, but these two equations kind of simplify the algebra for you. So use those. Take a look at this checkpoint number 8. Now, when we have collisions in two dimensions, everything's the same, except now we have to look at stuff in the x direction, we have to look at stuff in the y direction. So we're going to have to use our trig functions to split up our momenta into the x and y direction. However, energy does not change, because remember, energy is a scalar. Direction doesn't matter. We only have to split up momentum because momentum is a vector. Take a look at checkpoint number 9 here and give it a try. Now, we're going to deal with some systems that are a little more complicated in that their mass changes. Easiest example of this is a rocket. Well, why does the mass of a rocket change? Well, the rocket is using full fuel to propel itself. It's burning fuel to exert a force on the gas, which is the gas then exerts a force back on it. But as it does this, as it burns fuel, its mass changes, and so as the mass decreases, that pushing force actually has a greater effect. Or, to keep a constant velocity, we need to have a smaller force because the mass is changing. So looking at the conservation of momentum, that the initial momentum is equal to the final momentum, we can rewrite it as, well, the initial momentum, the mass, the total mass, this is big M, times the velocity, has to equal a negative dm times u, okay, and we'll talk about what that is in a second, plus the total mass plus dm times v plus dv. Okay, now this looks kind of complicated at first, but it's a nice simplified equation that's going to help us out here. Now U, we can rewrite U, and U, don't get this confused with potential energy. U is actually talking about the speed of the mass that we're losing. So really, this term right here, this first term, U is involved in this first term, and that first term is the linear momentum of the exhaust product that's released during this time interval. And so we're losing some momentum from the rocket in that exhaust product. And so we have to take that away from the momentum to, get the end result. All right, because really, because remember, the momentum of the system has to stay constant. It's what this originally was, but we're kicking some exhaust back, and so that's going to propel us forward, and so that's why we have that negative sign here. So in using that, in using this this equation back here and defining U as this here, we can come up with the first rocket equation here, in that R, which is the mass rate, okay? So that's the mass rate of the fuel consumption, okay? And that's going to be given to us in, usually kilograms per second, all right? We multiply that by the relative velocity. Now we're talking about the relative velocity of the gas and the air, all right? Or excuse me, the gas and the rocket, the relative velocity between the gas and the rocket, the exhaust of the gas coming out of the rocket. That will equal the total mass of the rocket times its acceleration. And so that's what's kind of unique, tricky, and elegant here. From this complicated equation here, we can simplify things to a nice, simple equation if we look at the mass rate. Now, if you want to derive that and see where that comes from, it takes a little bit of algebra and some stuff, and you can even look at a derivation in the book if you'd like in Chapter 9. But the left side of this equation is what we call the thrust. All right, that's the thrust force. All right, and that's how much force we're getting out of this. And we can derive the velocity change for a given consumption of fuel as the second rocket equation we have here, looking at this in that our change in velocity, so we can either write this out as Vf minus Vi, or delta V is equal to the relative velocity times the natural log of the ratio of the two masses, the initial mass divided by the final mass. So that ratio of masses, take the natural log of that, multiply by the relative velocity, and that's going to give us the change in velocity of the rocket. Now notice what's happening here. It doesn't matter what the mass of the rocket is, except for the ratio of the initial to final. We can find that change in velocity just by taking that ratio. So these next few slides here are a great summary of Chapter 9 and all of the equations, and all the key equations are highlighted here on these two slides.